Okay, we'll get started. Just a few logistical things about the quiz. I'll grade these and I'll post the grades online as soon as possible. We will not have time to go over the answers to the quiz in class. There's also 5 versions, so we just won't have time to go over all 5 different versions of the quiz. I also, after I grade them, you can contact me to come during office hours to review your quiz, okay? So you are allowed to review your quiz next week during office hours. Just send me an email letting me know that you want to take a look at your quiz, because otherwise it will just be lost in the stack of papers. So send me an email and I'll pull your quiz out so you can review it. I don't let students keep their quizzes because I do reuse questions or similar questions for future classes. However, I don't feel like I am depriving you of a study resource, because I feel like the practice quizzes that I've posted online are well representative of the actual quizzes. So if you want to take a look at the quiz next week to see what you've gotten wrong, that's no problem. Just send me an email and I'll pull your quiz out of the stack and have it ready for review during office hours. Okay, are there any questions about that? Yes?
Should we, is it okay to email you an hour before, or is it something we do right now?
Yeah, send me an email at least, I'd say the day before, okay? Just give me a little bit of advanced warning, okay? I mean, it doesn't have to be, you don't have to email me now, but at least the day before, okay? If you send me an email 1 hour before, I probably might not see it in time to have it pulled out. Yes?
Are all quizzes 30 minutes?
Yeah, pretty much all quizzes will be 30 minutes. There will be maybe a couple exceptions where I give you maybe 35 minutes, but most of them you can estimate about 30 minutes, and you can expect the practice quiz and the actual quiz to be fairly similar in that regard. Okay, so as far as study guides for the future, I'd say look at the practice quiz, because I know I don't let you guys keep the actual graded quizzes, okay? All right, so today we'll wrap up Chapter 2 and enter Chapter 3. We are still in our section on descriptive statistics, okay? So today will be more descriptive statistics. We are covering Chapter 2 and 3. Just to recap last week, we covered the nature of data, okay? And we said the kind of the big picture idea of statistics is that it allows us to make conclusions from limited data, okay? So we can make conclusions about the population And I kind of broke down the course, and I said, there's 3 parts, or there's a few different sections. One is we begin with descriptive data. We first learn how to describe data. And then once we've learned how to describe data, which is what today we'll cover, we're still in kind of the section of descriptive statistics, we will cover probability. And with our understanding of probability, then we can combine descriptive statistics and probability to perform statistical inference. Okay, so last week we covered describing categorical data. Okay, we could summarize categorical data using what kind of table? So we have a frequency table. That's one way to summarize categorical data, and then we also learned the two-way table if we have two categorical variables. Okay. And then as far as graphic displays for categorical data, what do we have? A bar chart. Okay, so for graphics, we have the bar chart. Okay. So that's kind of a recap of last week. Okay, and so this week, we're going to learn how to summarize numeric data. Okay, and so to summarize numeric data, we will have a few graphics. Okay. So as far as graphics go, we have a dot plot, a histogram, and we'll also learn the box plot. And we will also have numeric summaries. Numeric summaries, or what we might call sample statistics. And these include the mean, the median, the standard deviation, and the interquartile range. Okay. All right, and again, all of these things, just this is for numeric data, okay? Okay, so let's start off with talking about what a dot plot is and what it might look like. Okay. Okay. So a dot plot is one way for us to display numeric data. Okay, so one of the thank you for closing the door there. One way to display numeric data. Okay, and the idea behind a dot plot is that you have a number line to represent kind of represent where the location of the values. And you will have you have one dot for each observation. Oops. Sorry, let me just pull up my okay, and so here I've got here we have some data. Okay, you don't have to write all of these down. This is coming from page 39 in the second edition of the textbook. Okay. Okay, I've got a bunch of values. Okay, these are how many goals a soccer player scored in a season. Okay, this is a college soccer players. Okay, so these are the number of goals scored. Okay. And so, you know, we had someone who scored 9 goals in the season. This person scored 11 goals. We had actually 4 people who scored 11 goals. We had one person who scored 12. We had 5 people who scored 13. Okay, and so we're going to represent this with a dot plot. And so a dot plot looks like this. Okay, we have basically kind of a dot at for each observation. So we had, you know, here's the one person with 9 goals. That person is represented by this dot here at 9. These 4 people with 11 goals are represented by these 4 dots right here. The person with 12 goals is represented by this dot at 12. The 5 people with 13 goals are represented right there with 13 goals. Okay, and here we have 3 people with 14 goals, 2 people with 15, and you know, 4 people with 16 goals. All right. We don't have anybody with 17 goals, so at 17 there's no dots listed. We have 18, 19, and 20, each with 2 goals, and 21. Each with 2 people. And at 21 there's 1 person, and then there's 1 person who scored 35 goals. And so, you know, when you look at just the numbers, it's kind of hard to see exactly kind of the typical number of goals scored or things like that. However, when we display it in a dot plot, we can see, you know, kind of the average, the quote, typical number of goals is around 14 or 15 goals. It is about 14 or 15, okay? And then we also see the dot plot shows really how remarkable 35 is compared to everyone else, okay? Okay. And so this is the construction of the dot plot. I think it shows our data, and we can see all the individual values there. Okay. We can easily create a histogram in a similar manner. Okay. And so here's the dot plot. Okay. And I can easily turn this into a histogram, but instead of having dots, I'm going to turn them into bars. Okay, so here's a dot plot, and using the same data, we can go and make a histogram. All right, and so let me just show you what a histogram would look like. So with a histogram, I would create little bars to represent the height of these things here. Okay. Oops. Okay, and then so if I have all of these bars, then this is a histogram. Okay, and so I'll color these in here. Okay, and I think you guys get the idea here. Okay, and so we get rid of the dots, but we have bars that represent kind of the height. Now it's a histogram. Okay, so we have bars to show the height rather than dots, and now we have a histogram. Okay, so we have bars to represent how common or how frequently we observe a particular value. Is that okay? So that's a histogram. Now, it might seem like, why would we bother with a histogram? It's presenting the exact same information as the dot plot, and that's a valid argument. There's one advantage with the histogram, is that with histograms we can also bin together values. Okay. We can bin values together. So let me illustrate what I mean by that. Okay, so we can say as far as goals go, we can bin particular values together. We can say I'm going to create a bin for 9, 10, and 11. And then I'm going to count the frequency. So when I look at the dot plot, I see 1, 2, 3, 4, 5. There were 5 people who scored either 9, 10, or 11 goals. And then for 12, 13, and 14, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 people who scored 12, 13, or 14, okay? And then so I would do 15 through 17, 18 through 20, 21 through 23, 24 through 26, 27 through 29, kind of 30 through 30, 32, and 33 through 35. Okay, so for 15 through 17, I've got 1, 2, 3, 4, 5, 6 people. For 18, 19, and 20, I have 6 people. 21 through 23, I have 1. And at 24 through 26, 27, 30 through 32, I have 0. And at 35, I have 1. Okay. And so I can take these bins and make a new histogram. Okay. So we'll say histogram based on the bins. And I just want to make sure that the creation of these bins is okay. Are there any questions on this? All good there? Okay. And so, oops. Yeah. So when you create the histogram based on those bins, your resulting histogram will look like this. Okay, and we can see that indeed all I did was I took the exact same data that was in my dot plot, okay, and I just created bins, okay, and so we can see between 9 and 11 here, okay, and so the the bars start at kind of the left edge, so 9 through 12 or 9, 10, 11 we have a frequency of 5. 12, 13, and 14 we have a frequency of 9. 15 through 18, 6. 18 through 21, 6. 21 through 24, or 21 through 23, 1, okay? 0, 0, 0, and then 1 again. So the histogram, these two histograms have the same underlying data, even if they appear a little bit different, okay? Alright. But the histograms still reveal the same things. Even if the histograms themselves look a little bit different, we would still say that kind of the typical number of goals seems to be around 15. This seems to be about kind of the halfway mark, and it seems also the case with even with the when the goals have been all binned together, okay? And we can still see that the score of 35 is quite different from everyone else. Okay, so that's still apparent, even though we've changed the size of the bins between this histogram and this histogram. And as far as histograms go, okay, or not as far as histograms go, but when we're talking about numeric data. So we've basically summarized a sample of data, or we've created a graphic display. We can even just kind of even further simplify a bunch of data. So here, here's a dot plot that show, we looked at a bunch of different law schools. Okay. And we asked each law school, you know, what percentage of your graduates pass the bar exam? Okay. And so a lot of law schools, the percentage of students who pass the bar exam is something around 85, 90%. Okay. So we have a lot of law schools where, you know, 85 to 90% of their students are passing the bar exam. Okay. And that's probably expected. We would expect students who graduate from law school to become lawyers, okay? But, you know, we have, this appears to be a law school where only about 30% of their graduates pass the bar exam, okay? And it makes you wonder how much learning is happening at that school. And, you know, and here's another school where only, you know, less than 50% of their students are passing the exam, okay? And so, you know, that, to me, that would be a strong case that this school is not educating their students, right? You know, students pay tuition to attend law school and they're hoping to become a lawyer, and if only 30% of their students are passing the exam and not becoming lawyers, or I mean, only 30% move on to become lawyers, you have to question how good these law schools are, okay? Because it seems like the vast majority, you know, over 80% of students are passing. Okay, anyway, we can summarize this graph. Rather than showing all the dots, we can summarize with a simple curve. And so we might say the shape of this graph looks something like this, okay? And we would say that this shape is what we call left skewed. Okay, and left skewed, you can just imagine, you know, if you had cut this out from the screen here, or you know, cut it out, and you were to skewer something, so maybe a piece of meat, you would use the left side. Okay, the left side would do the skewering. This is called the tail. You can think of it as the skewer, okay? This is called the tail. But that's the side that you would do, you know, do the stabbing with, and so this is called a left skewed distribution, okay? And so what does it mean to be left skewed? It means, so left skewed generally means, you know, most of your scores are going to be kind of on the, you know, you kind of have this bulk of scores, okay? So think of where the bulk of scores are, or the bulk of observations are, okay? So think of where bulk of observations are, and so in this case this would be kind of the 80s to 90s, right? Or 80 to 95, that's where the kind of where the bulk of the observations are located. And left skewed means that there will be some extreme values to the left, or much lower than the bulk of the observations, okay? To the left of that bulk, okay? And so to the left means having lower values. Okay, because when you look at the number line, you always start off with small numbers to the left, and as you move to the right, the numbers get larger. So left skewed means that you'll have some extreme values to the left or much lower than that area of where the bulk of the observations are. Okay, so this would be an example where what percentage of students passed the bar exam. You're going to have some schools where you've got very low percentage rates, okay? And you're not going to have any schools higher than 100 because it's impossible to have a higher than 100% pass rate, okay? That's the best you can hope for, right? Graduates of your program, all 100% of them pass. That's pretty good, okay? And you're not going to get better than that. And so that would mean, that's what it means to be left skewed. Okay. So what would right skewed mean? Okay. Yeah, so right skewed would look something like this. Okay, this would be right skewed. Okay. And that means, you kind of have the bulk over here. Oops. Okay, so the bulk is over here, and then you have some extreme values to the right. And to the right means having larger values, right? Some extreme values to the right or very large. So an example of data that is right skewed would be income. Okay, so income, most people probably make between $30,000 to $100,000, okay? $30,000 to $100,000, okay? And we'll just say with quote typical average being something like 60,000, okay? All right. Can someone make $1 million a year? Yeah, okay, so 1 million per year. And so if we say average is 60,000, 1 million would be 940,000. So 1 million is 940,000 above average. Okay, are we going to have any values that far below average? No. Okay, as far as the amount someone can be paid for a wage, that the lowest amount would be minimum wage, or we might have unemployed people making $0, okay? But as far as a job, you can't be paid a negative thing, okay? And so 1 million is 940,000 above average, okay? No one can make like 940,000 less than average. So it means you've got extreme values to the right, but not in the other direction. So that would be something that's right skewed. Yes, question?
So this graph shows that the average of yearly income is actually 60,000?
I'm just ballparking that number.
Oh,
Yeah.
Because I'm trying to see how to use the graph that makes sense. But
Okay. And we're just saying kind of, you know, most people in the U.S. will be making somewhere between 30 and 100,000 or something like that. You know, maybe I should extend that to 150,000 or something. But you know, most people are kind of be in that range. And but yeah, some people make $1 million, or some people make 10 million a year, things like that. Okay. Symmetric. So this is still just talking about the shapes of numeric data. Symmetric would be something like this. You're going to have extremes on both sides. The bulk is in the middle. You're going to have some that are way higher than the middle and some that are way lower than the middle. So you can think of human height as something, an example of a symmetric distribution. Okay. You also have uniform distributions. Uniform means you know, kind of all of the values within the all of the possible values have an equal chance of showing up. Okay. So it could be something like, what are the last 2 digits of your phone number? Okay. And in that scenario, we expect any combination of 2 digits to be equally likely, okay? Something like that. And then we can also talk about modality, which is basically how many peaks appear. So if there's just one peak, whether it's left skewed or right skewed, we would say this is unimodal. Unimodal means there's one peak, and that means there's one, you know, one range of values that are most common. Okay. If you have something like this, this would be bimodal, okay? 2 peaks. And you would have, this means you have 2 different values that are most common. Okay, and kind of a, and there's like a dip in between, okay? Where, you know, you kind of have values in between these 2 peaks that are less common. Okay, and then anything with more than that, we would just kind of say is like multimodal. meaning we have several different peaks showing several values are very common. So something that's bimodal would be, we could ask, or yeah, I guess it would be multimodal, but we can ask people, you know, go to at home, how many tires do you have? Okay, how many tires do you have at your house? And you're going to get a lot of people saying, I've got four tires. You're going to have a lot of people say, I have 8 tires. Okay. You might have some people saying 6, right? Because they could have a car with 4 and a car with or a motorcycle or something like that. But you probably won't have very many people say 5 tires, okay, or 7 tires or something like that, okay? I don't know. I guess I'm forgetting to factor in the spare tire or something like that. Okay, but all right, so maybe you'll see a lot of people say I have 5 tires, or a lot of people say I have 10 tires or something like that. But you're probably not going to have a whole lot of people say I've got 7 tires or something, some strange number like that, okay? So you're going to see a peak at 5 for a regular car with 4 tires and a spare. And then you're going to have, you know, some people where they have 2 vehicles at home, so they're going to have a total of 10 tires. But, you know, kind of these in-between values are a little bit awkward, right? To have 6 tires means they've got a car with 4 and they've lost the spare, and they've got a motorcycle, or they've got, you know, a full set and an extra tire laying around or something. Like, you're going to have some people answering 6, but it's just not going to be as common. Okay, so you're going to see something where you've got peaks like that. Okay. Okay, so that is that covers modality. All right, and so that's those are just ways we can display numeric data. All right. Now, beyond just displaying them, we might want to have summaries. Okay, so this is now entering chapter 3. We're going to have what we call summary statistics. For numeric data. And so what a summary statistic is it's just a number that summarizes our set of data, okay? So, you know, we might just call these statistics for short, okay? But what is a summary statistic? Okay, it's just a number that we use to summarize a bunch of data. Okay, so you know we're familiar with the use of summary statistics for different aspects of our life. Okay, and so you know a common summary statistic for you guys is your GPA. Okay, it's just a single number that's supposed to summarize your entire academic performance, okay, or your entire academic career. And it's just, we take all of how you've done in all of these different classes, and we give you a single number, okay? We take the grade of your class, of each class, which in of themselves are summaries themselves, right? Like when you finish this class and you get a grade, it's a summary of how you've performed throughout the course, okay? And then the GPA is a further summary of that because, and so, you know, this just tries to summarize your entire academic performance. Okay, and so these summary statistics, they're most useful when we are trying to compare one data set to another, okay? So rather than having to look at all of the individual measurements in that data set or in that sample of data, we can just summarize it down to a single number and compare these numbers. So, you know, when you apply to a school for admission, they'll ask for your transcript because they might want kind of an idea of how you've performed, but they're not going to ask for all of the work that you've completed, right? They're not going to ask for all of the essays that you've turned in your different classes and all of the test scores you've got. At best, they're going to ask for your transcript, and oftentimes they'll just look at your GPA, okay, and they'll look at the GPA of one student, the GPA of another student, and use those to make quick comparisons. And so a lot of times, schools, when you transfer, they'll say, you know, your minimum GPA has to be this, right? Like a 3.0 or whatever if you're applying to a certain school. And basically, they're hoping to use that as a way to kind of filter the field, okay? And it's just a way to quickly make comparisons from one student to another, okay? And that's basically what summary statistics do, okay? So when making comparisons, between different samples of data. Okay, so we can summarize the you know, a student using a GPA, and maybe it's not a good idea because it doesn't tell the whole picture, all right? But with summary statistics, that's what we're trying to do, is we're trying to just kind of simplify our lives so that we don't have to look at every single observation in there, okay? This is often used in sports, okay? So when, if you ever watch, you know, a sports game on TV, they'll often flash up kind of summary statistics about a certain player. And they'll say, you know, for example, and during the NBA Finals, if you guys watch that, there's a player, Steph Curry, and he had a very good performance throughout the regular season, okay? And then during the last, you know, 7 games where that determines which team is the champion, his performance was not as good, okay? And so rather than trying to, you know, show a replay of all of those other games, they would just flash up things, and they would say, like, Steph Curry's, you know, shooting percentage, 3-point shooting percentage during the regular season was this, and during the finals it was this lower number. Or Steph Curry's points per game during the regular season was this, and during the, you know, the games in the finals it was this lower number. And that's just a way to kind of compare how the player was playing during the regular season versus during, you know, the finals. And so, you know, all that is it's just a single number, or maybe just a few numbers that are supposed to capture the overall performance of a player, okay? And they do this for football, baseball, you know, pretty much every sport. They've come up with little statistics, okay? You know, when we're talking, if you're talking about politics and things like that, they'll say, you know, under this policy or under this leader or whoever, you know, the economy, you know, went up or went, you know, was doing well or was doing poorly. And they're not going to try to give you every single detail about the economy, but they'll use just certain values that are essentially summary statistics. They'll say the unemployment rate was this, and it's just a number that's supposed to capture how well the economy is doing. Or they'll say, you know, the amount of this or whatever, you know, the GDP, or, you know, the you know, purchase parity index or whatever. They just have these different numbers that all kind of do something specific that's supposed to summarize something very complicated into just a single number that we can say, look at this number and look at this number. This number's bigger and that means this, or something like that, okay? Or you know, when you want to go watch a movie, right? You go on the Rotten Tomatoes or something, and it'll say the tomato index is 95%, and you're like, oh, that's a great movie. Tomato index 34%, that's a terrible movie, or something like that, right? And what is that? That's just a summary statistic. It's just a number that's supposed to summarize all of these other people's reviews, okay? Saying like, these people gave it positive ratings and these people gave it negative ratings, and we summarize that into just this single number or something. And you make choices about whether or not you're going to spend your money to watch a movie based on that. Sometimes, right? Otherwise, sometimes you're just like, I'm a fan of Batman, so I'm going to watch it even though people say it was bad or whatever, you know? But so, you know, summary statistics are useful, okay? And so, you know, don't get scared of these names like the standard deviation. All they are is just summary statistics that just summarize an aspect of our data, okay? So they're most useful in making comparisons between different samples of data, and again, it's just a number that we use to summarize a bunch of data. Yeah, question?
I notice you don't use the word average. Is there a reason for that?
No, I use the word average all the time, okay? But just...
You use it to summarize. That's how I was thinking, is this...
Well, so we'll talk about averages right now. So okay, so we have we have kind of generic summaries. Okay, so I've given you a bunch of kind of tailor-made summary statistics like the tomato index and your points per game and things. Those are all specific to a certain scenario, right? Tomato index only makes sense if you're talking about movies. It doesn't make sense to say my friend has a tomato index of 42, which I don't know. We don't do that, okay? But we have kind of these generic summary statistics, quote unquote generic summary statistics that are useful in any situation where we have numeric data. And so we have statistics. So I might just call them statistics rather than saying summary statistics every single time, because we usually mean the same thing. So statistics to tell us about central tendency. And so these are the mean and the median. And this is kind of our concept of average or typical values. So what values, are at what could be considered a typical value that we might see. So if we're talking about the gas mileage for a vehicle, a typical value is something around, 25 miles per gallon or something like that, okay? Okay, and then we have statistics. Oops, I had too many letters there. Statistics that tell us about spread or dispersion. Okay, and these are the standard deviation, in the interquartile range, or the IQR. Okay. Our book says that for skewed data, or I should say for symmetric data, we might prefer to use the mean and standard deviation. And it also says, for skewed data, we may prefer to use the median and IQR. Okay, but in reality, we can use the mean or median or the standard deviation or IQR for any numeric data set, okay? Or any numeric data set, whether it is skewed or symmetric. Okay, and just a quick check on your understanding. What does it mean to have data that is left skewed? Left skewed means, so you've got the bulk of values on the higher side, and you've got some extreme values that are much lower. Okay, symmetric, or so skewed, left skewed or right skewed means you're going to have extreme values on one side, and symmetric means you're going to have extreme values on both sides. Right? Okay, let's take a 5-minute break here, and then we'll come back and we'll finish up our discussion on summary statistics.